Good evening to one and all. Today we are here to celebrate May 12th, International Women in Mathematics Day. The day is in honor of Mariam Mirza Khani, born 12th May 1977, who is the only woman to win the prestigious Fields Medal. Today we will have a talk by Professor Barbara Lee Keyfitz from Ohio State University. Followed by her talk, there'll be an interaction with the speaker about the talk and also about issues concerning careers in mathematics research and women in mathematics in general. This event is organized as part of the May 12 initiative, which is supported and coordinated by several women math organizations across the globe, including IWM, Indian Women and Mathematics. So before I introduce our speaker, I would say a few words about Indian Women and Mathematics. IWM is a collective of Indian mathematicians that has been in existence since 2009. Our objective over the years has been to encourage more women to pursue higher education in mathematics and to organize events and networking opportunities that enable them to take up careers in mathematics. Since 2015, our activities have been funded by the National Board for Higher Mathematics, Department of Atomic Energy, India, mainly, and also by the International Mathematical Union's Committee for Women in Mathematics, partly. Throughout the year, we organize several activities such as regional mini workshops, mini courses, annual conference, visitor programs, mathematical workshops for young women, and also recently during COVID times, we used to have our visitor online lecture series. So without further ado, it's an honor to introduce our speaker, Professor Keyfitz. Professor Keyfitz is Professor of Mathematics at the Ohio State University since 2009, after 21 years at the University of Houston and 4.5 years as directors of the Fields Institute in Toronto. She received her undergraduate education at the University of Toronto and her MS and PhD from the Courant Institute, New York University. Her research area is nonlinear partial differential equations. Professor Keyfitz is a fellow of SIAM, Society of Industrial and Applied Mathematics, a fellow of the American Association for the Advancement of Science, a fellow of the American Mathematical Society, a fellow of the Fields Institute, and the recipient of the 2012 SIAM Award for Distinguished Service to the Profession. She has served on the editorial boards of several prestigious journals, including the AMS Proceedings, the AMS Transactions, SIAM Journal of Applied Mathematics, and a member of the Mathematical Reviews Editorial Committee. In 2012, she was the Noether Lecturer at the Joint Mathematics Meetings. She received the 2005 Prager Nelson Prize of the Canadian Mathematical Society and an honorary Doctor of Mathematics degree from the University of Waterloo in 2010. She was president of the Association for Women in Mathematics in 2005 and 6 and was a vice president of SIAM from 98 to 2003. And of the American Math Society from 2011 to 2014. From 2011 to 15, she served as the president of the International Council on Industrial and Applied Mathematics. It is our privilege to have Professor Keyfitz accept our invitation to speak on this day. And today, Professor Keyfitz will speak on partial differential equations, a way to get from here to there. So I am excited to hear your viewpoints on this vast and very important and diverse field of mathematics. So over to you, Professor Keyfitz.
Okay, well, thank you very much. And first of all, thank you for the invitation and for the honor of speaking to this group. I'm a little intimidated by the distance between us and by not knowing any of you. I hope that some of you will at least stay around after the talk and tell me a little bit about yourselves. Anyway, you heard many things about me, and I'm I'm not as impressive as all that sounds, but I'd also like to, in some sense, I'm welcoming you to my home because I'm giving this lecture from my house because the technological interface is a little bit better here, and I hope it won't fail us. I hope you can see my slides, and I will get to the business of telling you what I want to talk about. So I am beginning by assuming that most people in the audience don't know much about partial differential equations, and part of the objective of my talk is to try to convince you that this is a really interesting subject and something worth knowing more about. So to begin with, obviously from the name, a partial differential equation involves partial derivatives, which means you have to have a function of more than one variable. And we start by, this should work, thinking about what is a function of, let's say, two variables, and I will be dealing with two in this talk. It's the smallest number bigger than one, smallest integer bigger than one. Okay, so one way to think of it is as a, oops, I hope you can't see this. I opened the chat. Somebody asked if there would be a recording, and I believe it is being recorded and will appear sometime. Okay, so one way to think about a function is as a surface. And I've tried to draw this in 3 dimensions. Again, this interface is not perfect for displaying 3 dimensions, but a cusp is a sort of interesting surface because it's very much not 2-dimensional. And if you happen to have a piece of paper in front of you, you can fold your piece of paper to look like a cusp, as I have done here. I could have made a movie, but I wasn't sure how it would show up in the technology, so I didn't. But here are several perspectives of it. And in most of my talk, X will be the space variable, and this is the x-axis, T is the time variable, and U is some property that varies with space and time. In this particular case, oops, yeah, this was what I feared would happen. In this particular case, it's simply the property of lying above the x-axis. So it's a surface. And the equation of this particular surface, u cubed minus tu plus x equals 0, is a standard equation for a cusp. And as you can see, it's a surface. Now, of course, when we're talking about differential equations, we're actually talking about functions. And this surface is not necessarily a function. In fact, this particular surface is a function when t is negative. And I can see that it's a surface. Oops. Oh dear. I think I have accidentally gotten us out of this. Help. Sorry. I seem to have paused the screen sharing. Let me resume it. Okay, there we go. All right, I will not do that again. Here we go. Okay. The surface defines a function as long as u is a single valued function of x and t, and that's the case when t is negative and is not the case when t is positive. You can see that above every value of x and t when t is positive, there are 3 possible values of u. This is not completely incidental to my talk. It's a nice example, but we will see this coming up again and again. Okay, so the talk is about differential equations. So I keep seeing messages in the chat, but I'm going to have to ignore them if this needs to be interrupted. Somebody.
The Professor Keyfitz, you don't have to worry about the chat. We will take care of it later.
Okay, yeah, good. All right. If there's
Yes,
anything
please carry on. Yes.
yeah, thank you. Yeah, if there's anything I have to worry about, you tell me.
Yes, sure.
Okay, so the talk is about partial differential equations, so we have to talk about partial derivatives. And if you think about it, the partial derivative of u with respect to x, say, means the rate of change in the direction x, also known as the slope of the line tangent to the surface in the direction x. So here's my surface, and I tried to draw a line. It's not terribly clear. In this talk, I will be indicating space derivatives either as a partial derivative here, du by dx, or as d sub x of u, or briefly u sub x. And this is, engineers don't talk this way, but mathematicians do. U sub x in this talk means du by dx. And time derivatives similarly are du by dt or u sub t. Okay, so given a surface, you can calculate the partial derivatives just by differentiation. And the problem in PDE is, given the equation involving the derivatives, reconstruct the surface. And that's why I suggested that the talk is going from local to global, getting from here to there. Here is, we know what's happening right here. There is, I'd like to know what's happening all over the place. Okay, so I'm not making this stuff up. Partial differential equations occur in very important ways in physics and engineering. And just to try to intimidate you a little bit, I've written down the full set of equations for the compressible ideal gas dynamics in 3 space dimensions. This is an incredibly important system. I won't spend the talk telling you all the ways it's used. But for example, making airplanes fly, making nuclear reactors work, making understanding what causes and hurricanes and how they evolve, and so on and so forth. So these equations, there's an entire field of mathematics called computational fluid dynamics, and much of it is spent computing solutions to this system of equations. Okay, and so what is it? We have 5 variables here: density, components of velocity and pressure, and you can think of air or water or a gas. And it's a system of equations. The subscripts are partial derivatives. And it says that this combination of partial derivatives of these 5 variables and functions of them equates to 0. So everything is a function of the 4 variables, 3 space variables in time. The 5 equations express conservation of mass, momentum, and energy. The first one is mass, the second, third, and fourth momentum, and the 5th energy. Again, each of these things is still a surface, but now, of course, it's a function of 4 variables, so you need a 5-dimensional space to draw this. Nobody ever does that. And the surfaces are all coupled because each function appears in all the equations. Okay, in this talk, we will focus on a small corner of this. In fact, I took the very top corner and threw everything else out. If I just have rho is the density, rho sub t plus rho u sub x equals 0. And then I make it even simpler by assuming that the velocity u is a function of the density, in this case, half the density. I get a much simpler equation, and much of the talk will be about this equation. This is actually a very famous equation called Burger's equation. Burgers was a Dutch mathematician who first published work about this equation in the 1930s. He thought it was a model for turbulence, which is a very important physical phenomenon. It's not particularly, but it's a really interesting equation. Okay, and now just to relate it to something that you might be able to get a feeling for, I will relate it to a very appealing and sometimes useful example of one-directional traffic flow. So imagine traffic along a one-way street. This is sometimes called the Lighthill-Richards-Whittam model. It was their idea, and they had some practical reason for thinking it might describe how traffic works, so you can decide for yourselves. So here's my street, right? The street is the x-axis is now the street. And I look at the number of cars in this patch from X to X plus H, a mile down the street. And so the amount of traffic there is I just look at the number of cars between X and X plus H, and I'm going to model this as a continuum. So I'm thinking really of density of cars, not individual cars. And the total amount of cars in that interval is just the integral from X to X plus H of the density. I'll call that T. Now, how does that change in time? It changes, it increases when cars come in on the left, and it decreases when cars go out on the right. And if I measure how many cars, say cars per minute, are going in and out at each of those places, I call that thing Q. In engineering terms, that's called a flux. So the flux of cars, Q, is telling me how the number of cars in that interval is changing. So I get a nice equation here. It says for any H and any X, the rate of change of this integral is the difference between the two Q's. All right, we use a little calculus. Take the MVT is the mean value theorem. Mean value theorem for integrals says I can replace this integral by the length of the interval times some representative value in the interior. And now my the integrals disappeared. I divided by H. I do what every calculus student would do. I send H to 0. And then this representative point becomes X. And the Q term becomes a partial derivative. And lo and behold, I have a partial differential equation. Of course, it's not quite there yet because Q, I don't know what Q is. Suppose that Q, well, Q is always, the flux is always the density times the velocity. And suppose that I assume that the velocity actually depends on U. And this is the Lighthill-Richards genius. They said, suppose that the speed of the traffic really depends only on the density of the traffic. And I'll normalize things so that when the density is 1, the velocity is 0. That's when you have bumper to bumper traffic and nobody can move. And we know that happens all the time. And when the density is 0 or close to 0, the velocity is 1. So that's the fastest speed cars can go. And then you get this single equation for one variable U of one function U of two variables X and T. And in fact, it turns out this is the same as Berger's equation. If I make the simple change of variables, write U as 1 minus rho over 2, then the bottom equation at the bottom of the page turns into the equation at the top of the page. So I will be talking about these equations because they're interesting and because they're in fact related to each other, and I'll sometimes talk about one and sometimes the other. So let us go on. And now, of course, it's nice to tell you what an equation is, but we're interested in solving them. And so how do we do that? So let's start with a simple example. As in the picture on the last screen, I'll suppose I have just one space derivative, one time derivative. And now let me just suppose they're connected. I'll just add them to each other. I threw in a constant here. That could just be 1. I could just be looking at ux plus ut is 0. So now I should emphasize here that although I've been drawing surfaces, we actually have only one space variable. And if you've looked at it at any particular time, you're just looking at a one-dimensional thing, like a piece of string. So here's my piece of string. And let me suppose that initially at time 0, my string is has this configuration, just 2 little bumps in it. The solution to this equation basically turns out to be that the surface ut is just some function of x minus at. And if you think about what happens when t is 0, that function is simply the position of the string at time 0. So The surface, if I tried to draw it as a surface, would look just like this. I tried to draw a red line on this surface to indicate what it looked like at time 0, and this yellow line shows the configuration of the string at some later time, looks like 0.5. And you can see that all that's happening is that this wave is moving along the string. And I'd like to say something that I think is sort of interesting here, and again is part of the local to global theme. What the equation says is the rate of change of u, the rate of change of the height of the string in time, is simply proportional with the negative constant of proportionality to the gradient. So if I looked at a point on the string, here the gradient is positive, the slope is positive, so u must be becoming, u is decreasing in time. So every place where the slope is positive, u is getting smaller. Every place where the slope is negative, u is getting bigger. You could sort of think that maybe that's going to suggest a wave traveling with constant speed, but when you solve the equation, you actually see it. So that's again why people solve equations. They have this local information, how the string is behaving, and they want to know what the picture really looks like. Okay, so how do I find this solution? Okay, so now we have a short lesson in PDE here. How do I solve PDEs? And this, by the way, was something that I first saw as an undergraduate and in an ordinary differential equations course. And I was so fascinated by it that I decided to go to graduate school and study partial differential equations, which I have been doing for the last 50 odd years and still enjoying it. So without much primary motivation, maybe the only motivation is I don't really understand functions of 2 variables. Let me deal with a function of 1 variable. So let me suppose that everything depends on some parameter, some magic parameter s. X is a function of s, and t is a function of s, and then u, being a function of x and t, is also a function of s. And I can calculate the partial derivative of u with respect to s using the chain rule, du dt, dt ds, plus du dx, dx ds. And now if I compare the equation I was given with this chain rule, I just wrote one under the other, hoping that it would be clear that if I match up terms here, the ut has a coefficient of 1 here in dt ds, so I equate those. Here ux has a coefficient of a, or dx ds, I equate those. And did I lose my scribe? Yes, as usual. All right, and du dt is 0, so I get this system of ordinary differential equations. And let me suppose that I have to have an initial condition. Let me suppose I start at time 0 and just pick some point at random, x0, and look at what the value of u is at that point, u0 of x0. Okay, by now you've probably solved this system. You can see that the only solution here is that t must be the same as s. Here I'm just integrating the constant a, so I get x0 plus at. And here I'm not doing anything. U is just the same as value it had at x0. And this equation enables me to solve for x0 in terms of x. So I have this function. Now, and that's how I got it. Of course, I could have guessed it, but this is a systematic way of getting it, and we will see it becomes useful in another minute or two. Something I'd like you to see about this, because this is also important in the subject, is that, let's see, okay, sorry, is that I've found the solution. I found a solution that works for all time, and I found it without actually differentiating. I only integrated. Never in this whole development did I differentiate u0. So in fact, the solution I found works even if u0 is discontinuous. of course, if U0 is discontinuous, then the solution is discontinuous. And how can a discontinuous function be a solution to a partial differential equation? Well, you'd be surprised. That also turns out to be important. Okay, so before getting back to my real subject, which is equations like the one I just solved, I'd like to stop for a moment and say a little bit more about the partial differential equations I won't be talking about, equations that come from standard physics. And a more standard picture of a vibrating string is that you have a string that's under some kind of tension, and its motion is governed by Newton's law. Force is mass times acceleration. And I wanted to point out that this basically expresses conservation of momentum, which was part of the physical system I talked about before. Again, conservation principles and Newton's law play a big role in the derivation of differential PDEs and also in their solution, as it turns out. Okay, so where do I get this equation? Well, the mass times acceleration. Acceleration is, of course, the second derivative of position. Position here is the vertical displacement. The force is the net tension. The net tension on a stretched string, these little arrows indicate tension, and the force is going to be down because the net tension is downward, and it's roughly proportional to the curvature of this piece of string. You can imagine if the string is straight, there's no net force up or down. All right. So I end up with a second order differential equation, one with second derivatives. And again, this is very natural from physics, with a constant here that depends on the tension and the density of the string. Interestingly, this equation also has a very simple solution to write down, and I've written it here. It looks very much like the single equation I gave you, except I now have two functions of one variable, x minus ct and x plus ct. And again, here I think this is actually quite amazing as a local to global picture. The local physics, which was described by this equation or this physical picture, actually leads to waves traveling at a particular speed. Another way of seeing that, again, I apologize that my screen keeps moving. It's me. Okay, here's a fun fact, which is actually quite serious. I can factor this differential operator into d by dt of minus cdx applied to d dt plus cdx. And if you actually work this out in calculus, you'll see you get the factors. I factored it correctly. And now I can see, if you're looking at it from the perspective of the previous slide, here I have a transport equation with positive c, and here I have a transport equation with a negative speed, transport left plus transport right. Is this legitimate? As it turns out, it is. And just to show you what's happening is, suppose I had the same initial condition. What happens is that this little, this bump breaks into two parts. One of them travels to the left, one travels to the right with equal speed. And there we go. Okay. We continue here. Oops. Okay, now I have really messed things up. Let's see how we can get to the next slide. There we go. Okay, so just to, again, this is the last thing I will say about second order equations, but I wanted to point out that, in fact, you could, again, solve this wave equation by the same method of characteristics that I described earlier. If I factor it as I did, notice that if I actually had a solution to this part of the equation, that is to say, if this was equal to 0, then the whole thing would be equal to 0. So I would certainly get this part. But I can also factor it in the other direction. And then if I had a solution to this part of the equation, I would have a solution to the whole equation. So I'm going to get both those parts. And this is another important fact about this equation. It is linear, and I won't give the formal definition of that. It is linear in the sense that if I have two solutions, I can add them. An interesting question is, could the method of characteristics solve every second order equation simply by factoring? Well, turns out not quite, because if I had here's an arbitrary second order equation. If I wrote down the corresponding polynomial in A, B, and C, then the quadratic formula, which I assume you learned in high school, tells me how to factor this. And whether I get something sensible or not depends on whether I have a real or complex imaginary number when I take the square root. So suppose I had, for example, a plus sign instead of a minus sign. Then when I factored it, according to what I just said above, I would get a function of x plus it and a function of x minus it. So for example, I could have something like e to the I x plus it. Well, maybe. What does that mean? Well, it means something quite weird. Again, if you think about the wave equation, a rather standard solution to the wave equation is something written in the form of a standing wave, a function of a cosine, say, of alpha x, cosine alpha ct for any constant alpha. And before you say, but wait a minute, you told me that all the solutions were functions of x plus ct and x minus ct, I will point out that something that you probably also learned in high school is how to factor trig functions. A product of two cosines can be written as a sum of two cosines, and lo and behold, we're back to the other solution. Okay, so a very standard solution for the wave equation is these standing waves. On the other hand, if I got the equation utt plus c squared uxx equals 0, and you think back to the original model where I had this force pushing the string down when it was bent this way, what this second equation is saying is, well, actually, when the string bends down this way, this force pushes it upwards. Well, that's very unphysical. And indeed, it leads to some very unphysical behavior. If I start out with the same configuration of a cosine wave, then after a very short time, here time 5, the reason you can't see anything on this picture is if you notice the scale, my initial condition that had amplitude 1 now has amplitude about 150. This is not a very good model for anything that you expect to happen in the real world. So complex roots are basically unsuitable for initial value problems, and that's another subject which I won't get into today. Okay, so let me summarize the story so far. We've written a function of several variables as surface, a partial derivative as a slope. Let's go back, please. Oh, where did we get to? There we go. We talked about how local behavior, local information, which is what's happening at a point, can turn into a global picture by solving it. We noticed that if we really wanted to see what's actually going on, we need additional information like initial or boundary conditions. We noticed that derivations from physics give second order equations, sometimes coupled first order equations, and that there are different types of equations. Something that is implicit here is that for most partial differential equations, one can't find closed form solutions. We've left the world of calculus in that sense. On the other hand, the equations that do have closed form solutions can be a very useful guide to more general equations. I also should say that nonlinear and linear equations are very different from each other, and the rest of this talk will actually be about nonlinear equations, which is what I want to focus on. And I have mentioned several times that the physics often leads to equations that express some kind of conservation principles, and those turn out to be extremely important in nonlinear equations. So before I go on to finish the talk, I thought I would stop and see if there are any questions that I ought to answer, and I can now take a look in the chat and see if it's anything for me. No, well, apparently I can't when I'm sharing the screen. So should I?
So it's not, I think we can take up questions later. I don't.
Okay, if then I will continue.
Please.
Okay, so, all right. So let us move on to nonlinear equations, and I will go back to Berger's equation, which you may remember, u sub t plus u sub x equals 0. It's like a transport equation, but the transport is at variable speed. Suppose I apply the method of characteristics here. Turns out to be fun. So again, everything now depends on a parameter s. I compute the du ds by the chain rule. I compare the equation I was given with, I compare the two equations and I equate coefficients. I've written dt by ds as t prime to save space. So t prime is 1, x prime is u prime is 0. So I can actually solve this rather simple system of equations. S, of course, is t. U is going to be fixed. U at x0. U is just what it was at x0. The x equation is a bit more interesting because now when I integrate it, I find that x is going to be, well, I'm just, again, u is constant, so it's just u0, x0 times t. Now, when I solved the linear equation, I solved this equation for x0. Remember, I expressed x0 as a function of x and t. Well, that is the case, except I can't solve this explicitly anymore. So I can draw a picture. And here, so there are three pictures here. One is the initial condition. So this is what u is at time equals 0. This is u at time 0. This is what the method, excuse my incompetence. This is what the method of characteristics shows you for the solution, the characteristics of the solution. And if I tried to draw this, I can't, again, there's no explicit formula for it, but if I tried to draw it, I would see the cusp. So lo and behold, I have somehow or other miraculously found the cusp. All right. So in fact, that was no coincidence. This cusp is indeed a solution to Berger's equation. And let's see how, again, naively, implicit differentiation. I take this equation, differentiate with respect to t, I get an equation for ut. Differentiate with respect to x, I get an equation for ux. I notice that these equations are closely related. U sub t is minus u times u sub x, and I have Berger's equation. So the implicit function given by the cusp equation satisfies this particular initial value problem, where if I knew what u at x0 was, and in fact, if you look back on this slide, that is this function. Okay, so, okay, goody. All right, but as you may have noticed, we have a problem here. I do have a solution to the PDE for negative t, but not for positive t, because I have a surface, but I don't have a function. All right, how do we resolve this? we resolve this, and again, this is the beauty of this subject. We resolve this by going back to that original derivation from physics and saying, wait a minute, I differentiated this equation, but maybe I could have discontinuous solutions, and then I wouldn't differentiate, I would integrate instead. So suppose I did that, and I get into a mess of calculus here. Instead of differentiating the left side with respect to t, I integrate the right side with respect to t. Okay, so I integrate from t to t plus delta. Fine, I've got this, now I have two integrals. And now let me make a simplifying assumption that I just have two different values. The yellow value is u left, the red traffic density is u right, traffic density or whatever it is. And then I can carry out this integration, right? It's just arithmetic. And I get an equation that looks like this, which when I go to the limit of letting delta go to 0, I get ds by dt is q left minus q right over u left minus u right. And here s is the speed with which this discontinuity is moving. And I can do that. And again, the pictures are a little hard to follow, but if I did show them a little bit bigger. What I've done basically is take the cusp surface, and for positive time where I wouldn't get a unique value of u, I simply split it. I cut it in such a way that difference equation between the speed with which this is moving, which happens to be 0 in this picture, is equal to the jump in these quantities. So the one thing I'd ask you to observe is that, I don't know what this means. One thing I'd ask you to observe is that in order for this whole thing to work, I actually needed an equation that expresses conservation of something, because I can't equate these integrals unless I can integrate this. Fair enough. Okay. So this takes us into a subject that I won't explore in detail because it's this is where people spend their careers. The quantity that I found here, the solution that I found for this cusp is only in some somewhat vague sense a solution to a partial differential equation. A solution to a partial differential equation should have partial derivatives, and clearly this discontinuity does not. These things are called weak solutions because they satisfy the equation in that vague integral sense I suggested, but they are not what are called classical solutions, which are things that have derivatives. So there's a basic question. When do weak solutions exist? So what is known is that, in fact, the problem, as I described it, is not actually well defined unless I put in some further conditions. Mathematicians refer to this rather laughably as lack of uniqueness. It's really excess of solutions. One needs some extra rule, which typically comes from physics, to determine which weak solutions are actual solutions to the problem. This problem has been solved in some cases. For example, for Berger's equation, it's known that there's always a unique solution for all time as long as it satisfies. Hi, can you hear me?
Yes, there was some network issue in the middle, but we are back now.
Okay, right. Good. And for some reason I have lost your pictures, but
okay.
Oh, there you are.
Can you?
Okay.
Yes.
I can see that you're there. Okay, excellent. So, yeah, I was, I was trying to outline the entire theory of conservation laws in one slide. No wonder the system collapsed. All right, so we have, so the functions that we call weak solutions exist in a rather strange space, a space called BV, functions of bounded variation, which basically means if the function were differentiable, it would mean that the absolute value of its first derivative could be integrated and was finite. If the function has discontinuities, it basically means that the total amount of the absolute value, the total amount of jumps of discontinuities is in the magnitude is finite. For hyperbolic systems, that is the systems that have where the equations have real roots, in one space dimension, solutions exist when the data is small, close to, that is to say, close to constant in these this bounded variation norm. For linear hyperbolic systems, there's a complete existence theory in a different space, the space of L2 square integral functions. For nonlinear systems in more than one space dimension, nobody has a clue. We do not know. There is no existence theory. So the impressive set of equations that I wrote down at the beginning of this talk may or may not have solutions. Nobody knows what conditions one needs on them or what space they live in. In some sense, you may think this is discouraging. On the other hand, as mathematicians, we thrive on solving problems whose solutions aren't known in advance. So there's a whole field out here that waits to be explored. Okay. Let me talk, I think I have a couple of minutes left to talk about some of the more recent work that I have been looking at, although not as ambitious as trying to look at multidimensional problems. So to motivate it, I want to go back to the traffic flow model and look at a particular, so here I've looked at a particular set of initial conditions. We have an initial, this is traffic density. Remember, it was scaled so that 1 was saturation, 0 was empty road. And here I've started with a wave. The density is always greater than 0.5. It never gets above about 0.8. And so it's a lump like this. Okay. If I calculate the solution using the method of characteristics, and you can see the characteristic paths in the bottom slide here, bottom picture, the characteristics slopes are all negative, and I'll explain why in a minute. Remember the model, the model is modeling the density of traffic. It's not modeling what individual cars are doing. And if you think about it, you start with this symmetrically placed density function. The traffic's most dense right in the middle of this strip I'm looking at. And as time goes on, the densest bunch of traffic moves towards the back. That's because nobody can move very fast. The people at the front can move faster. The people at the back move slower. If you look at it from the purely mathematical, let's look at the characteristics viewpoint. The characteristic speed is 1 minus 2 rho. And since rho is always bigger than a half, this number is always negative. So the characteristics are always moving backwards. On the other hand, this is not what you as a driver experience when you're on the road. The driver is moving at the speed of cars at a density of traffic, namely 1 minus rho, which is always positive and certainly always greater than the speed of characteristics. So I've tried to draw here, just draw by hand, a couple of, this is what a driver would experience. They'd be going kind of, they're going remember this is x versus t, so the speed is the inverse of the slope. So when the slope is small here, the traffic's actually moving fast. Then it moves slower as you go through this bump, and then it moves faster again. But every driver eventually gets from the left to the right side. So this motivates looking at, oops, we went the wrong way. Oops, wait a minute, hang on. Yeah, sorry, this is where I wanted to be. And as you see, this is my last slide. Okay, so the current work that I'm doing with a couple of colleagues, John Holmes and Faraday Tigley, and also to some extent with my postdoc, Perona Duda, who is on this call, says, let's take a look at what this car is doing. So at time 0, let's say a particular car, this driver X is at position X, and his car, let's look at where that car is at later times. So that's y of t, and it's actually a function of x and t, which I will call gamma, but let me think of it just as its t dependence. So what's the guy doing? He or she, whoops, let's get back to that. Okay. Okay, so the rate at which he's moving, dy by dt, is 1 minus the density at that position, 1 minus rho of y and t. And I started at position x. So that's an ordinary differential equation. I can solve it. Sorry, you can hear me?
Yes, yes, we can.
Yeah, I lost. Okay, are we okay? Okay, so I hope you can hear me. I hope you can see me. All right, so here we go. The car is sorry. The driver has this ordinary differential equation. It turns out that you can also express this as a partial differential equation. So we were not the first people to discover this, but we discovered that you can write the this function gamma, which expresses the car position, the driver's position who started at point 0 or point x, and where he or she is. I should say she. This is a women's group. Okay, where she is at time t is can be found by solving this partial differential equation, which can actually be written as a conservation law. And I think I got a sign wrong here. I think this should be a plus sign and this should be a minus sign, but up to that. And rho 0 is, of course, the initial traffic density. So here is a second partial differential equation, which also describes what's going on in traffic. And the marvelous thing which we discovered is that you could start with this equation, solve this equation, and recover from it the solution to the original equation. So in short, there are two completely different ways of looking at this traffic problem, which give equivalent solutions. And it's a little deeper than that. In fact, a similar phenomenon is well known in fluid dynamics, where the description of a continuum of moving fluid can be described either from the point of view of looking at the density locally or looking at how each particle of the fluid moves. These are called Eulerian versus Lagrangian coordinates, and this quantity gamma could be thought of as a Lagrangian coordinate. There's a deeper connection here. This is connected to differential geometry because, again, this is a very simple picture of it, but this mapping from x to y, so think of this function now as telling you, given x, here's y. That's actually a one-to-one onto mapping of the road to itself. because every point on the road, there was a car somewhere before. Every car goes to some point on the road, and they're all different. So this is what geometers call a diffeomorphism, a one-to-one onto. Now, diffeo suggests it's differentiable. And here's the interesting point here. These functions aren't necessarily differentiable, so they're sort of weak diffeomorphisms, was the name we gave to them. This fits into a program that was originally started by Vladimir Arnold and taken up by others who've applied it to a number of different equations in fluid dynamics. And in one context, that is particularly incompressible fluids, which I haven't talked about, they have discovered that particle paths are geodesics in the infinite dimensional space of diffeomorphisms. Okay, so I can't draw any pictures of infinite dimensional space. That's why there are no pictures on this page. And explaining what a geodesic is in an infinite dimensional space is not a trivial problem, but it is one that we are trying to understand. In fact, we are currently aware of a recent result of Gessen and Michiolik looking at Berger's equation, but only at smooth solutions. And we want to see whether we can extend it to weak solutions. We haven't done that yet. If we do, and you invite me back, I will tell you how we did it. But this is where I will stop, and thank you for your attention.
Thank you very much, Professor Keyfitz. I hope I'm audible.
Yes, you were very audible.
Okay, so thank you for this wonderful talk. And there are two questions in the chat box, which I'll read out to you. So the first one is, can we check the uniqueness and existence of nonlinear PDE?
Can we check it? Well, again, of course, only theoretically, and there are many, so in many contexts, there are theorems that say this solution is unique. Uniqueness is always a very tricky question because, for example, if we look simply at Berger's equation and we say, is there a solution for all time? The answer is no, because there's not a differentiable solution for all time. Then you say, is there a solution for all time in this space BV where I define what I mean by weak solution? And the answer is, well, yes. In fact, there are many solutions. And in order to narrow it down, I have to basically, one imposes a certain condition of time irreversibility. And I didn't get into that in this talk, but you do have to do more work. And then the question becomes, okay, you say you found a solution in the space BV. Could there be a solution in some bigger space? And in many cases, people have been able to say, no, this is exactly the right space, and you shouldn't look at the ideal is to say, this is, if I put initial data in a certain space, I get a solution in exactly that space. In the case of Berger's equation, you can actually say more. You can give initial data that's not in BV, and there'll be a solution in BV. So I like your question, which was basically, are there ways of solving these problems? And the answer is yes. They tend to be very technical. There are good functional analytic tools for dealing with many of these equations, and many others basically techniques are invented to deal with particular equations. So the conservation laws, the best technique so far has been to solve very simple problems where you just had something like the picture I drew to motivate weak solutions. You just have two two constant states as your initial data. Can you solve that problem? Turns out you always can. And then can you solve more complicated problems by putting together solutions to these simple problems? And in one space dimension, that works, but nobody's been able to make it work in higher dimensions. And that's why the field is sort of stuck now. I hope that helped.
This question was by Sharikwa, and if you're online, you have another question on the chat. Would you like to
Let me stop.
interact?
Yeah, if I stop sharing, I think I can look at the chat. Let's do that. Okay. Okay. What about parabolic systems and elliptics? Yes. Well, the theory is very different. The theory in parabolic and elliptic equations have a much more advanced theory, and basically it's because typically they don't have to deal with weak solutions. Typically, solutions to elliptic and parabolic equations are what we would call classical solutions. They do have derivatives, and a lot of the issues that arise for hyperbolic equations don't arise. So in some sense, if you want a serene life with lots of satisfaction, work on parabolic and elliptic equations. Okay, let me work down here. Okay. Is it always possible to find the solution space of a given PDE? That is a great question. And that is the basic paradox of multidimensional conservation laws. That, as I said, the linear equations exist in the function space L2. Nonlinear equations, if in one space dimension, exist in this function space BV, which is fundamentally incompatible with L2. And nobody has been able to figure out, and I'm not embarrassed that I can't figure it out because nobody else can either, what the answer to this is. A number of people are now suggesting that the equations are basically ill-posed, that there's no definition of a good solution. I hope that's not the case. But let's see, when you mentioned particle pairs, are they geodesics and sensitivity? Are they more like geodesics? The problems that have been solved, they are geodesics in a Riemannian manifold, although it sort of depends on the category. If you want to work with C infinity functions, which is what a lot of people have looked at, then you're basically dealing with a Frechet space. You can make that into a Riemannian manifold, but it's a Riemannian manifold modeled on a Frechet space, and things like the implicit function theorem don't work. So defining what you mean even by covariant derivatives is an issue. This is something that I am trying to learn myself, and I sort of understand why it's an issue, and there are different ways of defining geodesics, and I don't know which one will work.
There is a question.
Oh, I see.
So Jyotsna, you can unmute yourself, please.
Yeah.
Hello?
Okay, go for it. Hi.
So, hi. I just, it's related to what Gautam asked. Can you please go to the last slide where you again mentioned about the particle follows
Okay,
because
okay, let me pull the slides back up. if I can again. Oh, where is it? I seem to have lost it. Well, let's see what happens. No. Oh, there it is. Okay. Yes. Yeah.
This particle paths are geodesic and infinite dimensional
Yeah.
space diffeomorphism. So I'm like it is the space of diffeomorphisms, and you are having particles which are identified with the diffeomorphisms and.
Okay. So yes. So the function that I called gamma, I don't know if you can still see this. So gamma, yeah. Okay. So gamma is a diffeomorphism of, say, either the real line or the easier model is to think of it as a traffic on a traffic circle. So diffeomorphisms on S1, which is a little, it's compact, it's a little easier to understand. Okay, so that's an infinite dimensional space.
Yes.
Right? D of S1, whatever you want to call it. And you think of the passage through time as a trajectory on that path, right? I'm sorry, a path in that space.
Okay.
It's
so for each fixed t, you have gamma x, which is going to be a diffeomorphism. You want
exactly, yeah. For each fixed t, gamma. It took us ages to get our heads around this. For each, in fact, I was going to try to draw a picture of it, and I gave up. But if you think. So one way of thinking of it, which is not too unreasonable, think about a traffic circle, okay? Which I'm going to think of, since I have to draw it, it's going to be the real numbers mod 1. So at time zero, you just have a straight line going from 0 to 1.
Yes.
As time moves on, your traffic, it's no longer a straight line. And it's no longer going from 0 to 1, but you always go mod 1. So you get another mapping back onto the circle. And of course, it looks nothing at all like the solution that I showed you, the traffic flow problem. It's not going to look anything like a cusp.
Yes.
But it's going to look like it's going to look more or less like that line going from 0 to 1. But wiggly, and every time you get a discontinuity in the solution, you get a discontinuity in the curve of that line. So it becomes a bi-Lipschitz homeomorphism of the line.
Because when you say a geodesic means, I was just thinking like what kind of like shortest path or a differential equation can one think of?
So so if you define a covariant, I mean, one way of defining a geodesic is through covariant derivatives. So basically, you want something that basically follows that path. You can also define it as an extremum of some kind of action function.
I would think of it much easier because if you do not have maybe just a distance minimizing curve would be a more
and that actually seems at the moment to be the best our best bet for making it work. And indeed, a number of people. I mentioned Hazen and Michiolik there, but many other people have pointed out that equations like basically a version of Berger's equation can be realized as a geodesic for the L2, basically the L2 metric on the space, but only only up to the point where you still have classical solutions.
Yes,
So
yes.
nobody has extended this to weak solutions, which is what we think should be possible.
Okay.
And I could mention again for people that are interested, but this wasn't. I didn't think this was. It would be possible to get into this. You can look at. You can look at other versions. There are other versions of equations that come from Berger's equation, where you add some kind of non-local terms, or even higher order terms like the Korteweg-de Vries equation. And some of these equations also can be made to correspond to geodesics in with different Riemannian metrics, like an H1 metric. So there's this is actually a pretty active field to try to find correspondences between different kinds of PDEs. As I said, it was really started by Arnold and pursued by Eben and Marsden and other people for incompressible flows. Incompressible flows differ dramatically from the compressible flows, which Berger's equation models, because they don't actually have real characteristics. They're not hyperbolic equations. So the question of how you would extend any of this stuff to hyperbolic equations is, it's an interesting question. But thanks for asking. Those are good questions. Those are good questions. Let's see.
Questions in the chat, folks.
I can't figure out whether I can show that it's fine chat or not. Here we go. Oh, now I think. Oh, so somebody asked, what is the cusp surface, which I showed in the slide? Okay, so I can go back, find a picture. Is that what it was? I seem to be getting an echo here. Yeah, I'm not sure what the question means. What do I mean by a cusp surface? Why is it called a cusp? That's actually a good question, and I don't know why this thing is called a cusp, but it's this thing. Just this geometry. I don't know why. Is that okay? So are there other questions?
Sorry, I think we lost voice in the middle.
Oh.
Yes.
Okay, sorry. Oh, I see. There's one question in here that I hadn't noticed before. Can we notice? Sorry. Oops. I don't know what happened in here. Okay, let me try. Can we apply the method of characteristics if we have a discontinuous initial condition? Yes, absolutely. But in order to do that, this sort of don't try this at home, kids. You'd have to understand what were these special admissibility conditions, which I did not discuss in the talk, and we could talk about that some other time, but I would. I mean, the answer is yes, but you need more information. Okay.
So I think we are done with the questions on the chat box. So so if anybody has a question regarding the talk, you can raise your hand. Otherwise, we can probably go to the second part of this event, which is to have a general discussion on mathematics, women in mathematics in general, careers in mathematics, so on. So I mean, what would be your advice to a young mathematician who is probably thinking of taking up a career in mathematics, and in particular, let's say if they want to study PDE, which is basically introduced at an advanced stage, not at the undergraduate level?
Yes. So, of course, there are many different areas of mathematics. Something that I know has been the case in India, and which has been, I think, unfortunate, is that there's, at least people have told me, that there's a sort of prejudice against what's called applied mathematics, and that this has been this has made it difficult for people who do things like PDE to get respect. I hope that that's changing. It certainly, I mean, I can tell you honestly that it used to be the case in this country, and in Canada where I grew up. I remember, well, you know, I graduated from college and I did reasonably well, and I went off to graduate school in the US because at that time there wasn't I wanted to study PDE, and that there wasn't much in Canada at the time. And I remember coming back after I got my degree and meeting one of my professors from college and telling him what I'd done. And I'd worked for a very distinguished advisor. And he said, "Oh, PDE, don't come looking for a job here." So it took a long time for the kind of mathematics that I do to be accepted. And it took a long time, in fact, for it to be accepted as applied mathematics. In the US these days, people are trying to be, people are becoming much more understanding that different kinds of mathematics all have their merits, all have their internal beauty. I mean, I work on the analysis of partial differential equations. I don't work on applications. I mean, I know there are applications, but nothing I do is terribly useful for applications. Other people, and that's just happens to be the way I feel about the subject. Other people are much more motivated by wanting to make a difference with mathematics, wanting to use mathematics to change the world. And you can do that too. I guess my advice really is find something that you enjoy doing and do it. We all have to think about earning a living and having a career and getting respect. And so you have to be somewhat aware of the parameters. When, and I can describe this from my own family, because my father was a mathematical demographer, so he knew some mathematics. He had a distinguished career as a university professor. I've had a very good career. My daughter, who was very bright, didn't want to get a PhD in mathematics. She actually is a computer scientist who works for Amazon, Amazon Web Services. She helps She helps make things like this work better. But I thought my father would be sort of embarrassed that his granddaughter didn't want to be a university professor. So I asked him about it, and he said, no. He said, not at all. She's made the right decision. He said, when I became a professor, it was the golden age. For you, he said, meaning me, it was the age of silver. For her, it's the age of lead. University teaching just isn't what it was. And it's no fun anymore. Do something else. So I'm not sure that's true. I have young colleagues who seem to be enjoying their careers. But one of the things that's very striking about doing mathematics these days is how much mathematics you can do without being in a mathematics department. We have people who graduated from my department who are now working in hospitals. They're doing research mathematics, but they're doing it on biomedical applications. So much of medicine and biology has now become mathematical that there are good jobs for mathematicians who want to help people's health. The internet, the World Wide Web has become an incredible place for people to do mathematics. After all, Google, as you probably know, was invented by mathematicians, and they hire huge numbers of mathematicians. Kristen Lauder, whose name you may not know, she's a computer scientist, mathematician. She was a former president of the Association for Women in Mathematics. She spent the first part of her career working for Microsoft, I think. She's now working for Facebook. So I assume everybody's heard of Facebook. And so, but again, working as a mathematician. I would guess that there are many career opportunities. And of course, I can only talk about career opportunities in the US. That's really the only place I know the job market. You probably, I am assuming that most of the people listening to this talk are actually in India and are thinking about jobs there. My guess is that there are very few unemployed mathematicians in India. They get jobs. And of course, again, something that you have to know is that it's not all fun and games, right? Doing research is incredibly frustrating, especially when you've got a deadline or you're supposed to be completing a dissertation, or even when you're just studying for an exam. It's not easy to learn stuff. And there are setbacks. Everybody has them. Let's see. Oh, there's a question. Is there any possible to do PhD? What is the eligibility? Well, there are many students from India doing PhDs in the USA. In fact, my first PhD student was from India. I completely lost touch with him. After he got his degree, he got a succession of miserable teaching jobs in the US, and eventually went to work for a company where he was very happy. Oh, I lost touch with him, but he stayed. He apparently decided he wanted to stay in the US and got eventually a very good job. you ask about eligibility. So about half the students in most PhD departments in the US are international students. So they certainly figure out how to get here. I guess, okay, so there's no central roster. You pretty much have to look at each individual university. I mean, there's no this is probably true for anything. There's no central place that you can apply and they'll match you up to the university that fits you best. You have to you'd have to look at different universities, and one way to figure out where you might want to study would be, so different universities have different specialties, right? I mean, some places are really strong in PDE, and I can tell you what they are because I know people in PDE. Other places are strong in number theory or analysis or computational mathematics, scientific computing. Sometimes you find out because you talk to your undergraduate professors, and sometimes you find out by looking at papers or reading articles. And then if you go to that university's webpage, the math department's webpage, you'll probably find, at least if it's like ours, you'll find instructions for how to apply, and there'll be a set of instructions for US students and a special set of instructions for international students. And almost every place, the deadline for applications is around the middle of December. Many places require some kind of the graduate records exam. These I don't know what you call them. We have just stopped doing it, but I guess they're standardized tests, is standardized exams. And again, each university will tell you what its requirements are. All international students have to show some kind of language competence. And even though probably for most of you, a lot of your undergraduate education was in English, you probably have to show that you've passed one of these TOEFL Test of English as a Foreign Language exams. And when you get here, okay, so the thing you need to know is that you get paid to be a graduate student, right? I mean, it is assumed that by the time people turn 21 or 22, they can no longer count on their parents' support if they ever could. And and they're not rich. In order to go on, they have to have some way of earning a living. And so most people are supported in graduate school as teaching assistants. And sometimes, if you can really impress the school you're going to, they'll give you some kind of fellowship so that you don't have to teach for a year or two. You can just concentrate on your studies. But almost all graduate students in math do teaching and grading for their departments. And so you, but again, you get paid a rather miserable amount of money, but people seem to be able to survive on it. The acceptance rates vary a lot. Some universities are highly selective, very few students get admitted. Others are do better. at Ohio State, we're sort of in the middle. We're a bit competitive, but we find that the students that we really want to have end up going to places like Harvard and Princeton. But we had some very good students nonetheless. I got a question here asking about becoming my PhD student. I'm not taking any PhD students anymore because I'm very close to retiring, but I certainly have colleagues who are interested in PhD students. And if you, I mentioned that the work I'm doing now, I'm doing with Faraday Tigley and John Holmes, who are both in my department and would be interested in having PhD students. So by all means, let us know. By the way, you may not be able to figure out, but Faraday is a woman mathematician. She's Turkish. We are always very eager to get women students. In fact, the entire mathematics community in the US has become focused on finding more women to become mathematicians. So that doesn't mean that every individual woman is going to have a good experience here, but the place, we are trying to be more welcoming.
So this last point that you raised about trying to get more and more women students. So not just in degree programs, but when women are competing for, let's say, awards or being on some important committees, generally they are made to believe that they are there because they wanted a women representative. So how is that issue in the US? Or you've been part of AWM, so I'm sure you are aware of the global situation.
Well, it's a problem and it's unfortunate because what can you say? I grew up in a world where I was one of the top 2 students in my class. I went to my department chair for a letter of recommendation for graduate school, and he said, I don't think girls belong in graduate school. So for people like that, anytime they see a woman on a committee, they're going to assume that that's why she was there, because she was a token. Fortunately, fortunately, the younger generation of academics generally recognize that those attitudes are old-fashioned, that women are on committees because, well, frankly, women are better committee members than men. women listen to other people, and men do. Well, I'm sorry. I know, I can see from the pictures that there are some men in this call, and I don't have anything against men. I love men. I love my male colleagues, and most. There is a tendency, let me just say, an awful lot of the things that women have to do because they're women, like balancing family needs with work needs, which men of the current generation often do too, but of the older generation, many don't. Women get more used to taking other people's perspectives into account, I think. I don't think it's any I don't actually think it's any natural difference between men and women psychologically, but at least for women of my generation, the experiences that we've had have pushed us to taking other people's perspectives into account. And I think that makes us more suitable to serve on committees. Or at least.
So how was your experience when you were at the top positions in SIAM or International Council on Industrial and Applied Mathematics? How was your experience there as a woman mathematician?
Okay, so my experience with ICM, by the way, was extremely good. First of all, if you haven't had the experience yourself, being the president of something is really great. Being the best experience I had in my life was being the director of fields, and it was the first time I'd ever really been the boss. I mean, of course, I wasn't the boss. There was a board of directors that was technically the boss, but it was really fun. You should try it. There were, and I don't think that I got that position because I was a woman. There were 3 people who applied for it, and the other 2 were men. I actually think I was the best qualified, and it never occurred to me. It's actually never struck me that I got any. I did get one position because I was a woman. When I was at the very beginning of my career, I was phenomenally unsuccessful. Okay, so you heard about all the successes, but at the beginning of my career, I was like, I was a total failure. I wrote a kind of cute PhD thesis, which could have been a lot deeper, but I didn't. I did something very superficial, which more or less fooled my thesis advisor, who I think didn't realize how superficial it was. I needed to stay in New York, so I got a job in an engineering department, and it wasn't a good position. There was nobody. I really didn't know how to do research. I didn't have anybody to work with. Those were the days. Okay, so I was an attractive young woman, and people wanted to socialize with me. They didn't take me seriously. They didn't want to talk about research. So after 6 years, I was about to be fired. I mean, I was about to not get tenure and be fired. And Kathleen Morowitz, who was a famous woman mathematician at the Quran Institute, one of my mentors, happened to be a trustee of Princeton at that time. And she noticed that the entire engineering school at Princeton had no women on the faculty. And she said, this is terrible. And this was 1976. There were already lots of women forming careers. And they said, well, there aren't any women. And she said, Barbara Keyfitz she won't gasify coal, but she's a darn good applied mathematician. By then I'd actually started to do some research. And she more or less bludgeoned them into hiring me. And again, it was only because, first of all, they needed to show a trustee that they could hire a woman, and she had pushed me. So yes, I got that job because I was a woman, and it was a temporary job. It was clear that I wasn't going to get tenure in an engineering school. I'm not an engineer. I actually had a wonderful time there. I did some really good research and eventually got a good job. And I'm extremely grateful to Princeton and to Kathleen for getting me this job. I don't know what I would have done otherwise. So I can't say I never got any help because I was a woman. I certainly did in that case. That's the only substantial help I got, I think, for being a woman. So one experience that I have, which again, it's not unique in this country, but it is somewhat distinctive, is that I'm also married to a mathematician. In fact, I'm married to a mathematician that Nikita knows, whose picture you can see here. Let's see, there he is. All right. There are many couples in the US where it's a mathematician married to a mathematician, and then it becomes a very difficult question. You know, getting jobs is an issue, right? Often we will, we've had the experience of offering a job to a woman, partly because we wanted to encourage women, but usually because she was very good. And then she would say, well, can you hire my husband? And so we actually, I have what's rather amusing about Ohio State. It's a huge university. We have zillions of departments and a huge medical school. And a number of my male colleagues were hired because their wives had been hired at the medical school. So we, the question of whether you're there because of your unique qualifications, you know, it can't be answered. Nobody's qualifications exist in a vacuum. You might be hired someplace because you're the only person willing to go work in Alberta. You might be hired because you're the only person willing to, what am I going to say, teach remedial math to people. I think who you are, your personality, is always going to play a role in your getting hired. I have a colleague, I had a colleague at Houston, I imagine Nikita will recognize this from the description, who had the firm belief that personality should play no role in your success and your hiring or anything, that really you could absolutely loathe and despise a person and share none of their values. But if they were a good mathematician, you had to have them in your, and they wanted to be in your department, you had to hire them. Eventually, he hired so many people in his field that he couldn't stand, that he had to leave and go somewhere else. So I think it's perfectly appropriate to take personality into account to a certain extent.
So, Keyfitz, Jyotsna has something to say.
I just wanted to say that it was nice to hear such honest replies, because it really helps a lot of us. Because of course I'm much senior to Nikita and all of them, so I think, and I'm junior to you, so I have been in that in between phase. So I have met Kathleen Moravec also, and Yeah, I have met her. Yeah. So I should say that, of course, I work in, I think we have met, but I do work in PDE, partial differential equations. By the way, maybe you can see
Yeah,
later.
when I saw your name there, it looked familiar, but I couldn't remember the context.
Yeah, because I worked with Isabu and the Italian group and Henrik and free boundary problems and those kind of things.
Ah,
Everything, maximum principle and those kind of stuff. So yeah, also, yes. You don't have maximum principle, right, for these kind of things, because
absolutely not. No, we couldn't live with a maximum principle in hyperbolic equations. It's against our principles.
okay. Okay. So no, I means, of course, I would like to add, as you said, that unfortunately, or I should say fortunately, somewhere or the other, if one finds what you are capable of, then you do get the right kind of respect, and someone helps you if you are working hard. That is what. And I just want to thank again that you shared your honest experience. But I think we have already here in India.
And you remind me that I really should say that I was helped tremendously by a number of mentors at the beginning of my career, and I'm eternally grateful to them. One of them, his name was Velvel Kahan, W.B. Kahan. He's a really successful computer scientist, but when I was an undergraduate, computer science was part of mathematics, and I took some courses from him. He was, to most people, seemed like an incredibly unpleasant person. People absolutely hated him. And the reason they hated him was that he made them feel stupid. He would ask these questions. He would challenge people to find the answer to something. But I loved it because all my the male undergraduates, they all thought they were so smart. And you really couldn't be sure, right? But if they couldn't answer questions any better than you could, then maybe they weren't any smarter than you were.
Yeah. I think this meeting, having these kind of people helps a lot in your career, like someone to just give the right push. And as you said, I think many of us women also don't have fear of giving wrong answer. I think so. I think that should be part of learning, because at least you are trying if you are giving an answer. See, whether something is right or wrong comes later. So
yes, yeah. No, people should never be mocked or put down for giving the wrong answer. When you volunteer to give it, in fact, that's actually really good advice. Volunteer. When somebody asks for an answer, answer.
Yes,
let them notice you. Yeah,
yes.
they. It's much better. It's much better to be the person who gives the wrong answer than the person who doesn't do anything. The people who sit in the back row are not going to get noticed.
Anyway, I don't have any more things to say, but it was nice listening to you. So yeah.
Well, thank you very much for coming and for introducing yourself. I think you're probably the person who should be telling this audience and giving them.
I tell them on and off whenever I meet them, because when I do meet some of them. Yeah, many times. So yes, I do. But it's always good to have, a third person perspective, you see. So because this is a good discussion, and the problems which we face are common. It's not going to be too much different. So yeah, it's okay. It's always good to hear from someone, again, your position matters and your achievement matters. So yes.
Yeah, and I'm aware of that. So even though I was really very unsure about what audience I would meet, and I'm hoping that not everybody who was listening was as well as informed as you are, because Professor Pradapat, because otherwise I would have given much too silly a talk.
No. I hit it. It was very nice. No. It's fine. It's fine. It's okay. No. I enjoyed.
Well, it was, I'll confess, it was a little disconcerting after talking about this to have somebody say, yes, but what metric would you use in that diffeomorphism space?
Gautam was also there, so it's fine. There are maybe they are not talking, but they are here. Yeah, they are here listening to you, so it's okay.
Okay.
So I think we are at the end of the event, but I will just ask you one final question, which is, how did you balance your work and life?
I wish I had it to do over again. I tell you what I would do more. I would enjoy my children more. If I was always so worried that I wasn't giving enough to my job. And I mean, fortunately, my children, they grew up fine. They're great. They're successful. I love them. They love me. But I wish I enjoyed them more. I was very lucky to be married to somebody who was extremely helpful, extremely supportive. In fact, I probably wouldn't have had children at all if he hadn't pushed it. It's good. Sometimes it's good to be married to somebody who's compulsive. So there were things I never really had to balance because I never was somebody who wanted a really exciting social life. I could imagine that if you needed to go out a lot with your friends and spend a lot of time doing stuff, you wouldn't have time to do mathematics. I mean, it does take time, and it's you have to balance. I think I worked very hard when I was young. I mean, I studied hard in high school. I studied hard in college. I studied hard in graduate school. And then there was a period of about 10 years when I really got nothing done. And so one of our graduate students here made a similar comment. He said, I worked really hard to get into graduate school at like this really young age, and I don't think it paid. So I guess part of this thing is like balance your time. There's certain stuff you can only do when you're young. My husband and I love sailing, and we now realize we've just got too old to safely take a sailboat out. And so I could say, well, I wish I'd started sailing younger. I would have had more time to do it. But, maybe I would have after 20 years, I probably would have got tired of it anyway. So when you're that young, think about the things that you can only do when you're young. If you want to learn to ski, do it now. Don't wait till you're 70. But one of my colleague, John Holmes, who I mentioned in this talk, is a very serious mathematician. He didn't want to be a mathematician at all. He dropped out of college. He became a short order cook. He finally somebody persuaded him that since he was good at math, why don't you become go into mathematical finance? That's a big deal now, right? All these people, a number of my former students are in the mathematical finance now. If you want to be rich, get a PhD in mathematics. So he thought he'd do that. And then he discovered he actually preferred doing mathematics to making money. So, you just have to live life as it comes, I guess. But don't forget that a lot of life is personal, and you want to have a personal life. I think it's important. And when you become teachers, don't forget your students. I mean, I can't see any of you. You're just names on the screen. And I'm sorry I can't see you, but possibly you're eating dinner or wearing your pajamas or something, and you don't want me to see you. I did. Thank you. I did teach for 1.5 years on Zoom, and I got used to looking at a screen full of names. And sometimes at the end of the call, at the end of the class, everybody would hang up, and there'd be 1 or 2 people there, and I'd know that they'd either gone to sleep or were playing a computer game.
Right. So yes, thank you very much for such candid conversation. I would say it was wonderful that you could talk about your experiences, about your life in such great detail. And I think that's what the audience wanted to listen, right? We were looking forward to having somebody who has achieved so much, who's been on at the top positions possible, and has also managed balanced work and life so well. So thank you so much for being so open while responding to questions and comments.
Thank you for setting this up, and keep in touch about your organization, IWM.
Sure. Yes, definitely.
If you're a real society, then you could join ISIAM.
Okay.
So yeah, we are not a society yet, but that is there in the future sometime.
Well, think about it, because ISIAM is an organization of societies, and admittedly, the focus is on applied mathematics, but we are always eager to get more members. I think that it's done a lot to help mathematicians around the world connect with each other, and I think that's important. So again, thank you all for coming and listening. And I have an email address. You can get in touch with me anytime. It was nice getting to know you.
Thank you so much, Professor Keyfitz, and thank you to all the audience present here. And Professor Keyfitz, have a wonderful day, and good night to everybody.
Good night.
Bye.